So we had this architecture, something known as the P2P networks. So in P2P network, suppose that you have created a block. Now that block needs to be mined in this network and needs to be added in the blockchain. Means that everybody is having their local ledgers, and local ledgers, that block will be added in each and every that block nodes in the blockchain network. So these algorithms requires that one of that node in that blockchain must be known as a leader node. So the leader selection algorithms must be there. So leader selection algorithms can be there. There are certain algorithms are there. So which is known as the secure leader selection algorithms that can do this task. So by which a leader will be selected over at node space. So if you don't have leader selection algorithms, you can probably run your round robin policy algorithms to select one node by one to give the each and every node as a leader. Okay. So suppose that you are having a leader, and leader has now a block. That block needs to be mined in the network. So then what this leader will do? That leader will send a block addition request with this block, and it will broadcast that block to each and every PR node in the network. So once that every node that receives this block from the leader, that every PR node needs to verify that block. So we have already told to verify a block that each PR nodes need to do the three things. We need to verify the mathematical, it needs to verify the current block as, and needs to verify the signature. And if these things are verified successfully, then only the PR node will send a valid reply message to the leader. Because the adding request came to the leader, and PR is sending a valid reply message once the block verification is successful. So assume that the leader is there. Later leader is maintaining a counter known as the receive counter. Initially it is 0. Now for each and every valid reply message it is coming from the PR node, this counter is getting incremented. Right? So therefore R count becomes R count plus 1 when a valid reply message comes to here, and so on. Now then what we are telling that suppose there are n number of nodes in the P2P network, and out of n number of nodes we are calling as the nth number of nodes is the number of faulty nodes. A node we are calling as the faulty nodes if it is faulty due to say power failure. Say some place the power play is there, so the server goes down. Or some node can be malfunctions or malicious, that could be taken as the faulty nodes. But this algorithm tells that if this round R count exceeds some threshold value, that is known as the 2NF plus 1, or in that it is meaning that when the 2/3 of the nodes in the P2P networks give the same valid reply message to the leader, then leader is ready to add that block in the blockchain. So in that case, what leader will do? The leader will send a commit message to all its PR nodes in the network. So once the commit message say this is from leader to say you receive it, then you confirm that okay this block will be added. So you are also adding your block in the local ledgers and so on. So in that way every node in the network say adding that block in their local ledgers. So that is known as the practical Byzantine fault tolerance approach. Is it fine? Okay. So then we are having another kind of protocol which is known as the RPCA, known as the Ripple Protocol Consensus Approach. So what it tells that every participating node or every PR node in the network they will maintain a counter or list known as the unique node list. So where that each node in the list will be considered as a trusted one. So this is a voting based mechanism. In the voting process what we have that every participant node will receive transactions from other nodes in the network. And it will verify the transactions. If the transactions is valid, then only it will integrate to another list known as the candidate list. So therefore I am the say node, I am receiving the transactions from others. I am gathering those valid transactions in a candidate list. Now I will say broadcast my candidate list to the others. So once I broadcast the candidate list to others, what other will do? Other will validate whether that candidate list transactions contained also in the local candidate list all the valid transactions are. If it is so, then what it will tell that the participating node sends the transactions that get more than 50% of the board to the others, and will tell that transactions has entered to the booking process. That meaning that if a transactions gets more than 50% of the boards from the others, will tell that transactions is entered to the booking process. Now next page is known as the probing page. So in the probing page, the same transactions or the set of transactions needs to be probed from say 50 to 60%, 60 to 70, 70 to 80% of this. So once 80% is there, that is threshold value, then we will tell that transactions will be added to a block in the blockchain other. So in other words, what we are telling that the participating nodes records the transactions confirmed by the 80% of the unique node list nodes to be added in the ledger data, and in that case RPC requires number of party nodes less than equal to d minus 1 by 5, where d is the total number of nodes in the P2P network, or what we want that this condition d must be greater than equal to I weighted plus 1 in case of the RPC algorithms, but in case of the EDFT we require 2NF process. So that is the difference. So apart from that, we had something known as the proof of work or proof of stack. So if we go to the proof of work, so that was the initial consensus algorithms proposed in the blockchain, and that is not actually energy efficient, because proof of work requires a very complex mathematical puzzle to be solved by the humans during the voting process, and that requires basically a lot of energy consumption to solve the mathematical puzzles. Right? And to remove that such kind of drawbacks, in the 2017 Ethereum, they proposed that alternative to the proof of work, something known as the proof of stack. So where it was designed to mitigate the limitations of the proof of work algorithm in terms of energy, cost, as well as processing. So that was basically the proposal which was given by Ethereum in 2017 as an alternative to the proof of work. So this is one of the examples where that Bitcoin or cryptocurrency works. So suppose that Alice has some money want to transact to the Bob, so therefore it creates a Bitcoin or cryptocurrency. Then the Bitcoin and cryptocurrency in terms of transactions it needs to be mined, which is a proof of work algorithm. And if this transaction is valid, then only the transaction will be added to a block in the blockchain algorithm. And once this transaction is say added in the blockchain, then we are telling that the transaction is complete. Either the Alice or Bob, they can always verify the transaction whether it is correctly put in the blockchain. Okay. So just like your Internet of Things, we are having the several applications of the blockchains due to the drawbacks of Bitcoin and cryptocurrency. Either it could be applied to the that is the smart manufacturing or supply chain, food industry, Internet of Vehicles or Internet of Drones environment, healthcare applications or smart environment. So that's why we are having some new terms, something on the blockchain of things. Right. Just like the Internet of Things. So these are some of the publications are there from my book. The list is old one. So first one that we applied the blockchain technologies for securing Internet of Drones environment, which was published in the IEEE Transition on Vehicular Technologies. Second one that we applied the blockchain for supply chains, which were published in IEEE Transition on Industry Informatics. And the last two was for changing IT environment as well as IoT including Internet of Drones environment for accessibility. these are the some key publications, and what I will do that I will talk about briefly about this work. Okay, so how this blockchain can be used in Internet of Drones environment. Okay. So as you know, just like Internet of Things, in Internet of Things, your things or objects are deployed in some certain areas, and they are connected to the Internet. They will gather the data information from the surrounding, and your data needs to be aggregated securely at some gateway node or access point, and your data needs to be stored in some say cloud storage or blockchain technology. So just like your Internet of Things, we are having Internet of Drones. Also, drones are also called as the unmanned aerial vehicles, and they will be say deployed in some time zones. Once they are deployed to time zones, they need to gather some information from the time zones, and those data needs to be brought back to something known as the ground state servers (GSS) for further processing, and GSS will say store the data in some cloud server or blockchain for further processing, for example, big data for this purpose. Now it has been shown that due to increase of the commercial drone and several applications, drones markets will be rapidly increasing. So for example, there was an estimate in 2020 that 100 billion USD market will be there for drones. As a result, we are having several applications for the drones. For example, it can be used in the military, it could be used in the gathering, where remote places news gathering is difficult, you can use the drones. It can be used for the agricultural purpose. Say US, they are using drones to spray the waters in the land, or even jump kits, all this they are spreading automatically using the drones. You can use that one. And for example, to supply say medicines to remote area hospital during say COVID time, etc., or even say traffic monitoring applications. Now the question is coming that what is the need for secure data delivery and collections need for the world? So in recent years, what it has been shown that drone delivery system helps in delivering your emergency goods. For example, your Germany-based DHL company was there, so they use the drone to say deliver say emergency-related items, for example, medicines to remote places. And in such kind of system, so one of the trust is there. There is a trust between the service provider as well as your something known as the customer. For example, say once is your delivery goods is delivered to your say house door, later you should not deny that okay, I have not received your items, or it has been stolen by somebody, etc. And also that customer needs to also rely the service provider. So then what happens that in practical scenario, this trust among the customer as well as your service provider, they do not stand strongly. So therefore a question comes that can we develop some secure delivery systems and collection mechanisms so that at any case neither the customer nor the service provider can deny that okay, your service has not been delivered or I am not received delivered, etc., etc. Later those questions will not come automatically. Okay. So for that reason, so we try to develop a secure system in Internet of Drones environment, so which will serve this purpose of the secure delivery of the collection. And of course that we are having a lot of struggle is there. For example, one of the main attack is known as the remote hijacking of drones. For example, say drones deliver an item to your doorstep, but somehow the attacker say hijack the drone, get all the information from the drones. Those informations can be used to capture the other drones, etc. Those kind of attacks are there. But still that we need, can we design a secure system that will give our better security. This is the work attempt to design a such kind of systems. So in this system, so what we have done that, so we are having several applications. For example, we are having agricultural applications where your drones can be flying in some this area, those data are captured by the drones. They can be securely brought to the downstream servers. The downstream servers can be connected to the control room and etc. etc. So finally what happens that so GSS they can form a P2P blockchain networks where the data received by the drones, they can form the transactions will be formed in the blocks, and blocks can be mined and put in the blockchain sectors for big data analysis. So here one of the purpose is that how to securely gather or collect data related to all the data delivery collections related transactions, and all the data in terms of transactions we need to put in the blockchain so that data nobody can deny all these things, and also those data can be used for big data analytics purpose also. So for this reason, so we are having the several pages. So for example, you are having registration authority. So who will be in charge of registering a control? So for that purpose, you require the registration process. That control room needs to send the registration request message. The registration details will be given to the control room, and control room for each and every applications. So for example, there will be control room for applications. It needs to register the GSS, register all the roles, part deployment. So that process needs to be also done. So for the digit, so your control room will involve all the drones part of the deployment. So that means that all the credentials then needs to be stored in the drones node. As well as the control room also register the constant servers. Now what we have done that, so after deployment for secure communications, a drone must communicate with the downstream server securely. So for that one, so we have adopted or we have designed something known as the access control mechanisms. So by which will be by the exchange of some messages, they will establish a session TCP, session P, and that session will be used for secure data delivery collections information to the downstream systems. So once downstream servers receive such kind of secure data, that it will form transactions, and those transactions will be used to form a block, and then the block will be sent to the leader in the GSS networks, and leader will run some consensus algorithms. We have also designed consensus algorithms. So that will be used for mining that block in the GSS networks. So finally that your data in the blockchain, and that blockchain data can be used for data for big data. So in that case, so we have used something known as the YouTube-based crypto systems. I am not going through that one. So pick up table is there, you can have this one. So for the registration purpose, so registration authority sends this information to the control room. For example, control room sends the information to the downstream servers. Control room rewards the information to the drone. So after they are having their all the credentials, they are now deployed and ready for secure communication. So this is basically something known as the access control mechanisms, by which there is exchange of the three messages between the drone as well as downstream servers. So first message, we have used something known as a certificate. Certificate of the drone is basically created by your control room, and the certificate along with the signature on the message that will determine that the message is authentic, as well as the message cannot be modified in between. So impersonation attacks, man in the middle attack, and replay attack is protected by your use of timestamp. So all the mechanisms are in place. And then message 2 also is there. In message 2 the session key verifier is there. It will verify the session key as well as it will give the acknowledgement. So finally if you see that drone and GSS, they are having the same session key between them for their secure communications. So once you are having say session key between the drone and GSS, for example, they can use now symmetric based crypto system, for example, advanced encryption standard algorithms, AES 128 for secure communication using this. So as a result, all drones, they are capturing information from the flying zones. All the data are encrypted and sent securely to the GSS. Okay. Now in this case we are having the various transactions in this form. So first transactions will be transactions CR GSS request. So it is basically meaning for data delivery request message from the control room to the GSS. So it represents a transaction between the control room and GSS. Then transactions will be the GSS drone request. It is a transactions between the GSS as well as drone. It is the data delivery request. We are having transaction drone to GSS response. So whatever that after delivering the things, collections, report, everything that needs to be given to the GSS securely. And finally, say drone will also capture some images from some certain area, for example, intelligent transport systems, traffic conditions, etc. That picture or video can be gathered, and those things can be securely brought to the GSS. So these kind of transactions we can have here, all these things. Now the question is that suppose we are having the transaction, GSS has transactions. Now once the GSS has, say for example, TN number of transactions, so it needs to create a block for mining purpose. So for creating a block, so what we are having that, it has a block header, for example it can have the block versions, previous block has, market root, we talked about already, timestamp, current timestamp, creator or owner of the block, then public to the sign up for signature verifications, and list of key and transactions. We have considered it in the private blockchain because the information are private for some activities, especially for healthcare activities. So therefore all the transactions are they are encrypted in the public key of the GSS. Then we are having the current block has and the signature on the current block. So those things are put in the block. Now once you are having block or GSS as a block, that block needs to be mined in the GSS networks in order to put in the block. So for that purpose, what we have done something like that, develop some consensus algorithms for block verification and decision. So in that case, what we have done that we have also chosen just like a PUP, we have taken a leader using some leader selection algorithms. So once a leader has the block, so what leader will do? Leader will generate the current timestamp for each follower downstream servers. Then it will create a voting request message, and voting request message as well as timestamp, they are also encrypted using the public key of the GSS or the GSS where it will be sent. So what the purpose is that, so we have created these consensus algorithms, secure consensus algorithms. That means that no information are going to be public and no attacker will know about your messages that in between during the process of the consensus. Okay. So once that this is the encrypted voting request as well as that block, they are given to all the peer nodes. What peer nodes will do, that peer nodes will decrypt using their own private key to get the voting request as well as timestamp. Then it will check that timestamp. Okay, that means the timestamp is place on. So to check the timestamp, for example, say I received a message in this timestamp, say TSS GSS one. Now say current timestamp is TS prime. Then I will check whether TS prime minus TS GSS is less than some threshold value, say delta T1. And if it is so, then I will tell that my message is place one. That this is not a old message I have received from the others. Okay. So once it is there, what I will do that, I will also verify the market root because it is in the block. I will verify the current block as and also signature on the block. And if the peer node finds that all the checks are successfully validated, then what it will do that, it will create a voting reply message as well as voting verification status. That block verification status could be either valid or invalid. If block verification status is 1, that means that all your checks are successful. Otherwise, so in that case, what we will do that all the peer nodes they need to send the voting reply message to the return node. So in that case, that all peer nodes they are encrypting using the public key of return. That voting request message earlier declared voting return message, voting reply message, voting status message. So once the readers receives this encrypted voting reply message from the peers, it is maintaining a valid count. It is initially 0, and it is now going to decrypt using its own private key. It is getting all these things, and it is checking whether the voting request message is previously matching with the original voting request message, and voting reply message is valid and voting status message is valid or not. If it is so, it is incrementing the counter of the result. And in that way, though, just like PBFT algorithms, we are checking this result counter that if it exceeds 2 number of quantity GSS nodes plus 1, then it is committing for block to be added in the blocks and others. And this is the procedure, and this algorithm is different from the other algorithms because it is a secure consensus algorithm. Okay, and attacker cannot know any information during the voting process. And it has been shown that it is reply attack protections is protected because we are using timestamps, and man in the middle attack is protected because we have used the certificates as well as signature. Similarly, that in-person attacks, what in-person attacks is telling that suppose sender is sending message to the receiver, in between the communications, attacker suddenly start communications on behalf of sender, and it is telling that okay, I have sent a message, and to force the receiver that this message is coming from the sender, but it is not so. But in this scheme, so in order to create such kind of valid message, the attacker needs to create the certificate or signature, which is not possible because that certificate creations and signatures require the private. That is not happening with the attacker. And here the don't capture attack, it is not possible because that if say drone is captured in this case, so what will happen that suppose a drone is captured. If the drone is captured, for each and every drone the certificates and private public key pairs are distinct. So therefore suppose this drone has been captured, adversary knows all the informations, but for all other drones the informations are distinct. So therefore adversary cannot compromise the other drones informations. As a result, the other drones informations attacks cannot be possible by capturing the information from a capture. So this is one of the good tool is that apart from the mathematical security analysis, so this is something like the formal security verifications using some software automated validation tools. So in that time we use something called the AICTE tool, which stands for the automated validations of internet security protocols and applications. But nowadays that we are having stronger tool, something called the SCYTHER tool, SCYTHER, SCYTHER. Those are also open access tool. You can install in your system. You can also implement your protocol. You can run also in the open system. Just like say for example we are having C programs, because I know C programs because we are old below. So C programs. So once you are having C programs, A.C, you are compiling it, you are getting A.out, assembler output, you run it, you get the output. Just like that, we are having protocol. So enter protocol you will first need to implement using something called the high-level protocol specification language, HLPC language. So if you need the code, so we can provide the code, but in principle it is not there. We are having. So that code basically needs to be compiled using a translator known as the HLPC2IF translator. That will give basically something in the intermediate format, just like your A.out output. Then AICTE that currently that supports the 4 kind of packets. One is known as the on-the-fly model checker, constant logic based attack searcher, satisfactory based model checker, key automata based protocol language. Now if you that feed your one of the backend, so for example if you run using the OFMC or CLATC, it will give the output format. Now output format precisely tells 2 things: either your protocol is safe or it is unsafe. If your protocol is same, it will give the statistics, how much time is required, how much depth or modes it has been searched, and how your protocol becomes safe. Or if it is unsafe, it will give the statistics. Also, there is a tool known as the span tool is there, annotated tool is there, which will also show that which part of the message on the fly that attacker modified so that protocol becomes unsafe. So that is a very strong tool, so that you can modify your protocol to have your strong access. So in our case, so we implemented the whole protocol, and then we compiled with this two backends, OAPMC as well as CS&IT, and it has been shown that so both the cases that we got the same result, that the protocol is same. And what is the limitations of the ATAC protocol? Forward verification tool is that it can only detect reply attack, man in the middle attack, and inverse attacks. Only three things it can detect, because it is based on Dole-Beow thread models. And Dole-Beow thread models is that it assumes that any two party can communicate about the in-sequential. So as a result, that any adversary can not only intercept the message, can also modify, update, or delete the message. And that's why that it can able to detect whether reply attack is happened or not, man in the middle attack happened or not, or in-person attacks. Only three things, not more. Then what we have done that, so we have implemented using something called Miracle library, known as the multi-precision, integer, and decimal arithmetic library, under the two platforms. First platform we have used that server setting. We have taken this one, so we moved to 80.04 with this memory, and we implemented each and every primitive. So this is known as the hash functions. This is known as the modular expositions. This is known as the elliptic point multiplications, elliptic point additions, and binary expressions. So what we have done that we run each and every primitive for 100 times, 100 iterations. From the 100 iterations, we have measured what is the maximum time, minimum time required. Then we have also taken the average time. Now, if you look at that the hash function is very efficient, because it is taking 0.055 milliseconds, and elliptic point multiplications is costly, and most costly person is that known as the binary table. It is very, very costly. So it requires 4.16 milliseconds. Now for the test bed experiment purpose, we have taken the Raspberry Pi, because that is the resource controlled CPU. So in that case, what we have done that in the Raspberry Pi, we have implemented each and every primitive, and those primitive code has been inserted in the memory, and then Raspberry Pi is connected to a terminal here. And from the terminal, so we have executed each and every primitive on the Raspberry Pi CPU. So what is the setting is there? Raspberry Pi, we have taken the Raspberry Pi B plus that model with these configurations. We also run the 100 times and measured maximum, minimum, and average time. And interestingly, if you show that, say even the for hash function time is more here, because Raspberry Pi speed, other things, etc. Not so much resources, that's our server platform is there. And most importantly, your binary pairing requires more time here, 32.0484 milliseconds time as compared to your server setting. It is 2%. So therefore, what is required that for building any protocol, security protocol, in resource control platform, you first need to decide that whether you are going to design energy efficient protocol or not, because that is most important. Otherwise, if you execute more complicated operations, it will go run faster and it will faulty very soon. Okay. So then we have taken something state-of-art solution with the U at all and D at all scheme, and it has been shown that so these schemes, parcels, and this board, we just go to the number of bits required in the communications. Then we have also done the executions, competitive executions for the skips, and these past two skips are based on bilinear pairing. That's why the cost is much higher. Our scheme relies on the input of distributed office, and this scheme is the best one because it does not require any input of distributed office. And then this comparison talks about the security functionality features. So which of the features can be supported in other schemes or not? Okay. So we listed in that time some of the features. For example, one of the good features is that something like the ephemeral security indicator under the secret adversary model. So what that attack tells that if your session key is constructed using both the permanent secrets and short-term secrets, then your session key is secure. Otherwise, under the secret adversary model, adversary not only eavesdropping all the message or modifying the message, also adversary can hijack a session. Once a session is hijacked, your random secrets you are generated in the time, that could be also considered by the adversary. As a result, if your session key is only based on the temporal secrets, then your session key can be leaked. Okay. And also that we did blockchain simulations. Of course, it is not the large scale one. Okay, the scalability issue is there. So in that case, what we have done that in the first scenario, that what we have done, we have taken the number of peer-to-peer servers as a 5. Because we done just in the computer, we created 5 virtual servers. And the number of transactions per block we have fixed as 60. But we varied the number of blocks mined in the network. So that means that we have taken a PTP network of 5 virtual servers. Each transactions, each block has 60 transactions. And in the first scenario, say suppose you want to mine the 10 blocks, and for that one person's algorithm takes how much time we recorded here, and for the 20 blocks, 30 blocks, 40 blocks, 50 blocks. And obviously when the number of blocks are more, so time is more, because when the number of blocks are more, you have to broadcast more number of blocks, and more number of blocks verifications are required more time, and etc. Okay. Therefore time also increases slowly when the number of blocks are. See, in the next scenario that we have taken that, so number of P2P servers at the 5, and we have fixed the number of blocks mined to be 30. But in that case, we have varied the number of transactions in the block. Okay. For first scenario, we take the number of transactions is 25. In that time, we recorded time. Number of transactions per in a block 50. Number of transactions in a block 75, 100, etc. So in that case also we notice that when the number of transactions is more, so then in the block that if you see that the market road verifications will be required more time because the number of transactions is more. Current block has time will be more, and signature verifications also will be more. Okay. And due to that, your time is also slowly also increasing. Okay. Yeah, so finally that we have done the real test bed experiment here. So in our lab, okay. Though it is not the large scale, but we have done something. So how practically this scheme works. So for that one, so what we have done that. So we have taken GSS, Johnson server as a laptop under this configuration. We have taken your a drone using the Raspberry Pi 3 configuration. Then what we have done, in this drone we have embedded a Raspberry Pi, and all the drones programs, whatever we have protocol, that program has been inserted here. Then we have here laptop, also from the GSS program point of view, all the programs are here. Then what we have done, we have created a local area network by using a router. So that router, railroad router, so they can communicate each other. And then the desktop is, laptop is connected to the Wi-Fi to our server. So that is taken as something say power server. where the data needs to. So in that case, what we have done that we have implemented our whole access control page or stream. Okay. So in that case, what we have done that. So this is from the drone side, this is from the Jesus side, and when a drone say is communicating with the GSS, drone and GSS, they first of all they use the access control mechanism, they establish a session key, common session. If you see that this is session key and this session key both are same, and this is basically the 256 bit session key because we have used the 3056 session key. So then for testing purpose, we have what we have done that suppose drone captures some images from the field manipulated. That image stored as a f2.jpg file, and that images is now encrypted using the AES 256 algorithms. AES 256 algorithms is the important. This is key, and the encrypted file was sent to this GSS, that is the laptop decrypted and stored the file and sent to the lab screens. So therefore, at least that we tried for the test bed experiment. So how really the protocol works. So in summary, okay. So at least that we tried to talk something about the blockchain technologies and its various applications apart from your Bitcoin or cryptocurrency. Then we talk about this case study where the need for data delivery and collections mechanisms for internet with drones environment why it is necessary, and then we talk about a case study skill using access control mechanisms. Then we talk about the blockchain simulations, what is the test bed experience, everything, and of course in the future that AI-based big data analytics using blockchain will be used to do. So yeah, so we have some time left. Yes. No.
The 10 minutes we can hang on.
Yeah. So just I'll go to this part only, a little bit of this one. AI-based big data analytics using blockchain. So what will be the implications of this AI-based big data analytics if we take the data from blockchain versus the non-blockchain or cloud-based? Just I will go to the things in a short, okay? Then we will wrap down. Okay, just I will give the very brief idea. So, what is the impact on blockchain-based, AI-based big data analytics for IT applications? So this work was done with my MTech students as well as PhD student Vasudeva. We now in US Singapore as a postdoc fellow. So it was published in the Complex Applications. Okay. So we have used in something on the cognitive Internet of Things. Cognitive Internet of Things, just enhancement of the IT, Internet of Things, where the cognitive decisions are useful for taking some decisions. That's all. So, likewise, your IoT, it has several applications. Either it could be drone delivery systems, rapid diagnostic, drone surveillance, wildlife monitoring, smartphone, etc. Now, what is the important is there? So, once we talk about the AI/ML here. So whatever AI/ML algorithms we can use, say deep learning, reinforcement learning, or CNN, RNN, etc., everything. But again, the heart of the AI/ML is that your training data. If the training data is not authentic or genuine, the whatever way you do the big data analytics, your assumptions or predictions is not done. Okay. And in recent years, that it has been shown that there are several attacks are possible in AI/ML. For example, first attack is known as the adversarial input attack. So here the adversary can crack the inputs in order to misclassify event detections. Another important learning is the data poisoning attack. For example, if we say stored simply in the trusted, semi-trusted cloud environment, say cloud environment, your the inside attacker can poison the data. For example, can say change the level of the data, can insert some fake data or some delete some data also from the database. So that is known as the data poisoning attack. So then the model attack or model steal attack. So in this case, the attacker can pollute the model's hyperparameter or can steal also the models to make the your predictions to be not accurate. So in that case, we have used as a case study the CNN, that is the convolutions neural networks. It has the three features, three layers, convolution layers. It reads the various features of the input image or input data. Once you are having the features, then the preliminary is there. That will basically to reduce the computation cost, size of the convoluted features there. And finally, we are having the fully connected layer that will basically make the predictions about the base descriptions of the input. So as a result, we are having the CS&IT architecture. So we are having the two steps. One is feature extraction, another is the classification. We are having input image to extract the features. You can reduce the features there, then finally classify. So in this case, what we are telling that if somebody does not use blockchain simple cloud server storage, due to simple cloud server storage, your data can be polluted or poisonous. So therefore, whatever this data that you take for the AI ML-based big data analytics, if the prediction is not accurate, so after that, whatever way you do the cognitive services here, the adversarial or action may not be. So however, instead of that one, if the data is stored in the blockchain, now we know the blockchain data is not polygons or immutable. Blockchain is immutable, so therefore, if you take the data directly from the blockchain, if you do the big data analytics and do the predictions, etc., that will be more accurate as compared to the prediction. So this study that talks about that. So what is the impact of AI/ML-based security if we take the data from blockchain or versus cloud storage, non-blockchain data? What will be the basically impact here? So that study is all about this paper.
So instead of from data we are taking from blockchains.
Blockchain. Not from the cloud server, we are taking the blockchain. Right?
Already in blockchain we have secure data.
Yes, yes, yes.
So that secure data we are trying to make actual predictions.
Yes, yes, yes.
So accuracy will be more in that
Yes,
case.
yes. We have just tried to show what is the implications. So in that case, we took about this block structure, block header, we have the block versions, previous block as market root, timestamp, sign-up block, block load, we told that transactions with signatures, and current block is mistake. So in that case, what we have done that after registrations, that drone will detect some potholes in the roads, and those data will be securely brought to the gateway node. Gateway node will collect all the data securely, aggregate the data. Aggregate data will be from transactions, and transactions from the transactions will create a block will be mined, stored in the blockchain, and blockchain data will be accessed for big data analytics. After that, cognitive science will be there for sending access of that. So in that case, what we have done that we have taken the database from the source, and for example, there are two databases there. Here it is the normal road and different portals, different cities, and this is the normal road, normal roads without any holes are here, different scenarios. Now we know that in the AI/ML, so you get to form the confusion matrix. So confusion matrix is all about the actual value versus the predicted value. So therefore, we can have the true positive, false negative, true negative, and false negative. For example, for the true negative, the observations, there is negative and predicted value is negative. All these things. And based on these values, confusion matrix value, we can have the accuracy, which is defined here. We can have the recall, we can have the precision, we can have the effort score. Right. Now, past experiment we have taken for the data positioning at something known as the noise salt insertion. So we have those database. In database, what we have done that we have inserted the noise, some noise in the database. Okay. So there are two things is there. So original data is there. So we are telling that original data where the percentage of noise is 0, assuming that it is taken from the blockchain, versus we have inserted the random noise, short noise. So for example, 10%, 20%, 30% in the database. Then we did the simulations or experiments. Then we have seen that the accuracy, recall, precision, and effort score, when the data is not corrupted, they are very high. But as well as your data is being corrupted, all the parameters goes.
Data is not corrupted in the sense data we are taking from blockchains.
Yeah. And versus that your data is there, you have inserted random noise, short noise in the data. So for example,
how do we insert noise into the?
For example, say here, so there is method say random short noise we can insert in the database. Okay. So you are having database, from the data we have taken database. So in the database we randomly insert say noise in some part, say 10% in the total database, 20%. We created such kind of database.
Okay.
Say for example, database around 10%, database 2, 20%, database 3, 30%. Then for each and every database we do the experiment. Okay. So what is the observation is that if the percentage of the noise is increasing, your performance of the system is going very rapidly down. Okay. And then also we did for the Gaussian noise, where Gaussian noise is a noise where that your the probability distribution is Gaussian or normal. Okay. So therefore, in that case also we see the same tendency when the data is taken from the blockchain. The performance are good, but when the noise is inserted, then the performance also degraded. Also, we took for the Poisson distributions, Poisson noise is there, same kind of things. But here we have seen that Poisson noise, this precision goes rapidly down at as well as effort score. So that effect more better. Yes. And finally, that we did the level flip method. We are having the data level that we change the flip, and in that case we have seen that also here these performance are very bad. Okay. So therefore, in summary, that what we are telling that when the data is not corrupted, data is taken from the blockchain directly, then in that case your the predictions about the accuracy, recall, precision, effort score are very accurate. For example, we are 87%, 86%, 85%, and 86%. But once is that your data being corrupted, your performance rapidly goes down. So that impact that we have shown in this paper, that the why that we need the security in the AI ML predictions. So that is very much needed, because you need to pass secure data or authentic data is very much needed for doing the predictions.
Which model you have taken for this?
CNN models. Okay. So this is all about that. Okay. Yeah. Yeah. Any questions? Anything? Any rapid questions? Okay, so if you have any questions, any query or any interest for research, so you can directly contact me in my email. So these slides are there, you can see it also.
I'll just share this.
Okay, all right.
Just say formal vote of thanks.
Yeah, yes, sure.
I, Nusrat Fatima, research scholar from Department of CS&IT, profusely thank
Professor Ashok Kumar Das sir for giving a valuable lecture on blockchain technology applications and impact of AI and ML on security. Thank you all. Thank you sir. Thank you for giving your time for us. Thank you.